Quality Systems in Semiconductor Equipment Manufacturing. Welcome to this overview of quality systems in semiconductor equipment manufacturing. These systems are essential for ensuring safety, driving performance, and achieving operational excellence. First, safety standards are foundational. They protect personnel, equipment, and the environment, and ensure compliance with international regulations like SEMI S2 and ISO 45001. Next is quality excellence. This involves meeting customer requirements, reducing variability, and consistently delivering high-performance equipment. Quality excellence is driven by practices like Six Sigma, FMEA, and ISO 9001. Process control is equally vital. Robust controls ensure that manufacturing outputs remain consistent and within specifications. This includes statistical process control, metrology, and monitoring tools. Finally, continuous improvement sustains long-term success. Techniques like lean manufacturing, Kaizen, and root cause analysis help identify inefficiencies and implement lasting solutions. Together, these pillars form the backbone of high-quality, reliable semiconductor equipment production. Introduction to quality systems. A quality system is a structured, systematic approach used to ensure that products and processes consistently meet or exceed customer expectations and comply with regulatory requirements. At its core, a quality system relies on documented procedures, effective controls, and a mindset of continuous improvement. The primary objectives are fourfold: to ensure consistent product quality, minimize defects and waste, enhance customer satisfaction, and maintain compliance with industry regulations. These goals support long-term operational success. There are 4 core concepts central to quality systems. First is documentation, having standardized procedures and records in place to provide traceability and consistency. Second is monitoring, which ensures continuous oversight of process performance. Third is corrective action, which focuses on identifying and resolving problems efficiently. And fourth is improvement, driving ongoing enhancements across all areas. A key insight here is that quality systems reduce variability and improve reliability across all stages of semiconductor equipment manufacturing. Critical importance of quality systems in semiconductor manufacturing. In semiconductor manufacturing, quality systems are not optional, they are mission critical. First, consider the extreme precision required. Modern process nodes operate at the nanometer scale, with 5 nanometer nodes demanding accuracy within a plus or minus 0.1% tolerance. A minor variation can lead to device failure or performance loss. Add to this the manufacturing complexity: over 1,000 tightly controlled process steps, exposure to hazardous chemicals, harsh environments like high vacuum and plasma, and production cycles that can span 3 to 4 months. Mistakes anywhere along this chain can be devastating. Financially, the stakes are enormous. A semiconductor fab often requires more than $20 billion in investment, and each wafer can exceed $10,000 in value. Poor quality can lead to wafer scrapping, costing $50,000 to $500,000 per incident, equipment downtime exceeding $1 million per day, and safety incidents whose human and operational impact is immeasurable. Quality systems help prevent these catastrophic outcomes. Critical importance of quality systems. Continued. Safety and compliance are essential pillars of semiconductor manufacturing. Quality systems ensure adherence to strict regulatory requirements that protect worker safety, uphold environmental standards, and conform to global benchmarks. Operations often run 24/7, demanding sustained performance and safety with no margin for error. A required yield of 99.9% reflects the industry's need for nearly flawless execution. Meeting these expectations is only possible through a robust quality system that tracks, verifies, and controls every process in real time. There is zero tolerance for defects. Even a single faulty chip can jeopardize entire product batches or customer relationships. To manage this, quality systems ensure 100% traceability, allowing teams to identify the exact point of failure and prevent recurrence. The critical insight here is clear. In this industry, quality isn't optional. It's the line between billion-dollar success and catastrophic failure. Effective quality systems are the foundation for sustaining this success. ISO 9001 Quality Management Standard. ISO 9001.2015 is the globally recognized standard for quality management systems, and it's foundational to excellence in semiconductor manufacturing. This standard defines the requirements for organizations to consistently deliver products and services that meet both customer expectations and regulatory obligations. Central to ISO 9001 is the PDCA cycle, Plan, Do, Check, Act, which drives continuous improvement through structured feedback and corrective action loops. The standard is underpinned by 7 core quality management principles: customer focus, strong leadership, engagement of people at all levels, a clear process approach, a commitment to continual improvement, evidence-based decision-making, and relationship management. Over 1 million organizations across more than 170 countries have adopted this framework. For the semiconductor industry, ISO 9001 delivers significant benefits. These include a robust risk management framework, streamlined process optimization, supplier quality assurance, enhanced traceability, and improved regulatory compliance. Collectively, these advantages contribute to long-term reliability, safety, and competitiveness in a high-stakes manufacturing environment. ISO 9001 Quality Management Standard. ISO 9001 is a global quality management standard that provides the essential framework for continuous improvement in the semiconductor industry. It begins with clear documentation. This includes procedures, work instructions, and quality manuals that ensure consistency and traceability in every process. Monitoring is the next pillar, focusing on tracking process performance and customer satisfaction to drive measurable outcomes. Training plays a critical role by strengthening competency management and skill development across all levels of the organization. Auditing completes the cycle, utilizing internal audits and management reviews to identify gaps and reinforce accountability. Together, these practices establish a continuous improvement cycle, yielding typical quality improvements of 15 to 25% after ISO 9001 implementation. Strategically, ISO 9001 acts as the foundation for building broader quality frameworks, allowing semiconductor companies to adopt industry-specific standards like SEMI S2. This alignment fosters a resilient and scalable quality ecosystem. SEMI Standards Overview. SEMI, or Semiconductor Equipment and Materials International, is the global organization that establishes vital standards for the semiconductor industry. Founded in 1970, SEMI today connects over 2,000 member companies and oversees more than 800 active standards. These standards span across several categories. Safety standards, such as S2, S8, and S10, ensure workplace and product safety. Automation standards like E4, E5, and E30 facilitate equipment communication. Material standards, C1, C4, and C8, govern quality and compatibility. Facility standards, including F40, F42, and F47, define utility and layout requirements. Standards also address gases, F1, F2, F4, silicon, M1, M12, M20, packaging, G85, G86, G88, and traceability, T1, T7, T10. SEMI standards govern a $574 billion global semiconductor market. The key benefits include equipment interoperability, global market access, risk reduction, support for innovation, and consistent quality assurance. These standards ensure that complex systems work together seamlessly and globally. SEMI Standards Overview. Most critical standards. Among the broad scope of SEMI standards, SEMI S2 and SEMI S8 are considered the most critical for the semiconductor industry. SEMI S2 provides essential guidelines for environmental, health, and safety compliance. It ensures that semiconductor equipment and manufacturing environments meet global expectations for protecting workers, facilities, and the environment. SEMI S8 focuses on ergonomic guidelines, promoting user-friendly design in equipment interfaces and layouts to enhance operator safety, comfort, and productivity. These standards are supported by a wide coverage across key areas, including equipment design, manufacturing processes, safety protocols, environmental controls, and data communication. SEMI's mission is to enable manufacturing excellence by leveraging global standards, fostering industry connections, and utilizing market intelligence. As a result, more than 95% of major equipment manufacturers comply with SEMI standards. This near-universal adoption creates a standardized language that enables seamless compatibility, collaboration, and quality across regions and companies. SEMI S2 Safety Standards. SEMI S2 is the foundation safety standard for semiconductor manufacturing, setting the benchmark for environmental, health, and safety compliance. First published in 1993, SEMI S2 is now mandated by 100% of major fabs and adopted in over 90 countries. It includes a comprehensive set of safety evaluation criteria. Electrical safety focuses on power systems, grounding, and isolation. Mechanical safety addresses hazards from moving parts and pressure systems. Chemical safety evaluates risks from toxic gases, corrosives, and pyrophoric materials. Radiation safety covers emissions from lasers, RF, and X-rays. Environmental considerations include seismic safety, fire risk, and proper ventilation. Finally, ergonomics ensures human factors and accessibility are considered in equipment design. SEMI S2 implementation has led to a 75% reduction in safety incidents. The benefits are significant: enhanced worker protection, lower insurance costs, legal and regulatory compliance, global market accessibility, and improved customer confidence in equipment safety. SEMI S2 Safety Standards. Certification process. SEMI S2 defines the minimum safety requirements for semiconductor manufacturing equipment, and compliance is mandatory for equipment acceptance by major manufacturers. The certification process spans 4 phases. It begins with an assessment phase focused on risk analysis. This is followed by evaluation, where standards are reviewed for alignment. Then comes testing, which verifies safety functions under real conditions. The final step is certification, which culminates in the issuance of the S2 report. Certification typically takes 6 to 12 months. Mandatory requirements include emergency stop systems, interlocking safety devices, gas detection systems, and seismic qualification. Documentation must include the safety assessment report, risk analysis documents, test certificates, and installation guidelines. Compliance is not optional. It is an industry requirement prior to equipment purchase. SEMI S2 is also linked to other essential standards like SEMI S8 for ergonomics, S10 for risk assessment, and S22 for fire safety, forming a complete safety framework. Conclusion and future outlook. The impact of strong quality management systems in semiconductor manufacturing is clear. Organizations are achieving a 50% reduction in defects, a 40% gain in efficiency, a 70% reduction in risk, and 95% customer satisfaction. Looking ahead, the industry is entering a new era shaped by Industry 4.0, where smart factory integration and real-time monitoring are transforming operations. Sustainability is also a priority, with green manufacturing and circular economy practices gaining traction. Advanced analytics, including big data and predictive insights, will drive informed decision-making. However, challenges remain: managing complexity, bridging skills gaps, integrating new technologies, and addressing cybersecurity threats. At the same time, opportunities abound: automated quality control, zero-defect manufacturing, real-time process optimization, and global standardization. Strategic priorities include digital transformation, AI/ML integration, sustainability, and talent development. The future starts with action. Begin with assessment, planning, and implementation. Quality is no longer just compliance. It's the pathway to innovation and excellence. Quality management components. An effective quality management system, or QMS, is built on an integrated framework that ensures quality across all processes. At the core are 5 essential QMS components: documentation, process control, training, and risk control. Documentation includes policies, procedures, and work instructions that standardize operations. Process control ensures workflows are well defined with clear controls and measurable metrics. Training guarantees workforce competency through certifications and up-to-date records. Risk control involves assessing potential issues, mitigating them proactively, and monitoring them continuously. The foundation of a successful QMS lies in core principles: customer focus, strong leadership, engaged people, a process-oriented approach, and a commitment to continual improvement. Implementation typically takes 12 to 18 months. Success is tracked with key metrics: customer satisfaction up 15%, defects down 40%, process efficiency increased by 25%, and a 20% boost in cost savings. Central to this system is the PDCA cycle: plan, do, check, act, which drives continuous improvement. ISO 9001 and key QMS elements. At the foundation of any effective quality management system is the ISO 9001 standard. This globally recognized benchmark provides the structure and requirements for consistent, quality-focused operations. A key component of ISO 9001 is auditing, which involves internal, external, and surveillance audits to ensure ongoing compliance and performance. CAPA, corrective and preventive actions, identifies and eliminates the root causes of issues, helping to prevent recurrence. Analytics also play a crucial role by tracking key performance indicators, identifying trends, and providing actionable insights. Management review is essential for strategic decision-making and continuous improvement based on data and results. Documentation is another pillar, including a quality manual, formal procedures, detailed work instructions, and accurate records. Critical resources for QMS success include quality managers, process owners, internal auditors, and training teams. With proper integration of all components, organizations can expect a 300% return on investment within 2 to 3 years. Integration excellence requires leadership, strong coordination, and employee engagement to sustain long-term quality improvements. Implementation challenges. Implementing a quality management system often faces significant barriers, many of which can threaten success if not properly addressed. Major challenges include resistance to change, which stems from employee pushback and cultural hurdles. Resource limits are another key issue, involving budget constraints, lack of time, and insufficient personnel. Technical complexity, such as integration difficulties and system compatibility, adds another layer of risk. These obstacles contribute to a medium to high complexity level, with failure statistics showing that many projects face delays, exceed budgets, or result in incomplete implementation. Risk assessment highlights training gaps, poor leadership, excessive documentation burdens, and culture clashes as common high to medium risks. Additional concerns include extensive documentation requirements, training needs tied to certification gaps, and the challenge of meeting multiple compliance standards. Despite these issues, an 85% success rate is achievable with proper planning. Effective solutions include structured change management to foster engagement, a phased approach to roll out QMS incrementally, and robust training programs to close skill gaps and enhance workforce readiness. Implementation challenges, failure points, and success strategies. Many quality management system projects encounter delays of 6 to 12 months due to a range of common failure points. These include inadequate leadership support, insufficient employee engagement, and ineffective communication strategies. Unrealistic expectations around timelines, a lack of dedicated resources, and poor change management practices also frequently derail progress. These issues are largely organizational rather than technical, highlighting the need for a solid foundation in leadership and communication. To overcome these obstacles, several best practices are recommended. Executive sponsorship is crucial. It ensures accountability and drives momentum. Establishing a dedicated project team creates focus, while maintaining clear communication and holding regular milestone reviews helps keep implementation on track. From an investment perspective, resource allocation should be strategic. 15-20% for training, 10-15% for consulting, 20-25% for systems, and 40-50% for staffing and operational support. Ultimately, leadership is the #1 success factor. Executive commitment plays the most critical role in ensuring a successful rollout. Benefits and best practices. Effective quality management systems generate proven results across industry-leading organizations, especially in the semiconductor sector, where 95% of Fortune 500 companies rely on them. The core benefits include cost reduction, which helps lower operational expenses across the board. Quality receives a substantial boost through defect reduction, directly enhancing product reliability and performance. Efficiency is another key gain, achieved through process improvements that streamline operations. Additionally, risk control leads to fewer incidents, improving safety and regulatory compliance. ROI achievement steadily climbs over time, as shown in the ROI timeline chart, demonstrating growth from implementation through to 36 months, eventually surpassing 300%. These benefits drive broader value in the business. Key value drivers include increased revenue growth, greater market share, improved customer loyalty, and accelerated innovation. These strategic gains not only justify the investment, but also position organizations for long-term success through value creation and operational excellence. Adopting these best practices leads to measurable, sustained performance improvements. Benefits and best practices. Achieving value creation and implementation excellence relies on a structured approach combining measurable success metrics with proven best practices. Key metrics include a 95% quality rate and a 60% faster time to market, reflecting high customer satisfaction and operational agility. A market leader position is supported by strong industry recognition and robust implementation practices. These include leadership commitment, where executive sponsorship and a clear vision are foundational, along with employee engagement through training and empowerment. Continuous improvement is emphasized through data-driven decisions, ensuring organizations stay adaptive and competitive. Supplier integration fosters a partnership approach, while process standardization ensures consistent methodologies. Regular auditing enhances compliance monitoring. These practices lead to impactful business outcomes: a 45% boost in brand reputation, 35% rise in employee satisfaction, full regulatory compliance, and a 98% audit success rate. The typical success timeline spans 3 months for setup, 12 months for full implementation, 18 months for ROI, and 24 months to optimization. Proven value. Organizations that implement comprehensive quality systems consistently realize significant returns on investment, typically ranging from 250% to 400%. These gains are not speculative. They are backed by measurable improvements in key performance areas. Quality systems directly enhance operational efficiency by streamlining processes, reducing errors, and minimizing waste. Simultaneously, they raise product and service quality, which in turn boosts customer satisfaction. Satisfied customers tend to be more loyal, make repeat purchases, and become brand advocates, further amplifying the benefits. Additionally, high efficiency combined with fewer defects lowers costs and accelerates delivery timelines. Altogether, this leads to a stronger competitive position in the market. By embedding a culture of quality, organizations establish a foundation for long-term sustainability and resilience. These practices enable companies to meet evolving customer expectations, regulatory demands, and industry benchmarks while securing a durable competitive edge. The data proves that quality excellence is a sound investment with enduring business value. Conclusion and future outlook. Quality systems continue to evolve, serving as a cornerstone for innovation in semiconductor manufacturing. These systems are not only a critical success factor, but also a key driver of competitive advantage. Organizations implementing them consistently realize a strong return on investment, typically between 250% and 400%. They also help mitigate risks by ensuring compliance with safety and regulatory standards. Looking forward, the technology roadmap highlights major developments: AI integration in 2024, IoT expansion by 2026, autonomous quality management by 2028, and quantum quality systems by 2030. Emerging technologies will shape this evolution. AI and machine learning offer high-impact predictive quality analytics. Digital twins are emerging tools that enable virtual modeling of quality performance. Blockchain is growing in importance for supply chain traceability. With a projected market value of $85 billion and a 15% annual growth rate by 2028, the global QMS landscape reflects a continuous evolution, underscoring that quality excellence is a never-ending journey. Conclusion and future outlook. The future of semiconductor manufacturing is being shaped by the ongoing evolution of quality systems from mere compliance frameworks into powerful strategic enablers. The impact is already measurable: 50% defect reduction, 40% efficiency gains, 70% risk reduction, and 95% customer satisfaction. These gains are driven by emerging paradigms like Industry 4.0, which brings smart factory integration and real-time monitoring. Sustainability efforts focused on green manufacturing and the circular economy, and advanced analytics, which leverage big data and predictive insights. However, challenges remain: managing complexity, closing the skills gap, integrating new technologies, and safeguarding against cybersecurity risks. Yet, these challenges also open doors to opportunities such as automated quality control, zero-defect manufacturing, real-time process optimization, and global standardization. Strategic priorities should include digital transformation, AI/ML integration, sustainability, and talent development. The path forward is clear. Start your journey now. Begin with assessment, move into planning, and follow through with full implementation.